It's all finite volume. So to me, it sounded like magic and I wanted to explore it. And then overnight, several companies started to contact us. But actually, we had no idea that it could be useful for so many people. In Germany, you often hear we have done this for the last 50 years like this, and it has worked fine. So we keep doing it like this. They totally don't care about the method that you're using. They care about that super reliable tool that always works. This was one of the cause where our software has been used in developing the drivetrain. So this kind of closed the full circle, and this was a really great moment. We tried to build general models, like general AI models, where we feed in a lot of simulation results. This has never worked.
Ladies and gentlemen, welcome to a new podcast episode today about the topic of smooth particle hydrodynamics, or at least some variation of it. We'll talk a little bit about the simulation type, how Martin has built shonDynamics, what China speed or like the China market looks like in terms of simulation, and what Europe can learn from it. So Martin, welcome to the show.
Thank you very much, Yusuf, for having me.
Super interesting. Before we get started, as always, Martin, can you give a little introduction to yourself? Who is Martin in the first place, and what are you doing actually with shonDynamics?
Yes, currently I'm based here in Karlsruhe. I'm recording from our office here. Karlsruhe is also the place where I studied mechanical engineering at KIT. I think just the same as you did. So you also know the city a little bit. After my diploma in mechanical engineering, I decided to do PhD. I also did it at KIT, and in my PhD, I focused on CFD simulation, multi-phase flows with heat transfer, so phase change, and also heat transfer in liquid metals.
Mm-hmm. The question that I have is, because I know KIT quite well, so did shonDynamics evolve from an academic research project, or what was the vision behind founding shonDynamics? What was the pain that you saw?
Yeah, the idea for exploring the method actually came from the academic background. And we pitched this idea to our professor back then, but unfortunately, you also know academia, there was no money for it. So it was seen to be too expensive to start such a deep project from fresh. So yeah, it was put to the trash, and we had to wait to fulfill our dream to explore this method until we were finished with our PhDs. So I'm already saying we, because of course, I did not build it on my own. At the beginning, I started it together with my business partner and friend, Shi Wang. And later, of course, many more people now are working on it.
Super interesting. We'll get to the China side of things in a couple of minutes. So how did you actually get started with shonDynamics? Right, you kind of incorporate your business, you get started. Like, what was some of the first big hurdles that you encountered while founding the business?
Actually, before we founded the business, we just made a small tech demo. Like I said before, we were super fascinated by this idea that we could get rid of the particle grid. Actually, when you are studying fluid mechanics, I'm not sure how it is now at university, but at least when I was taking the basic courses, nobody talks about particle method. It's all finite volume. So to me, it sounded like magic, and I wanted to explore it. And together we wrote a small tech demo about it to see if we can actually pull it together. And then my friend, he made just a small WeChat article about what we did, put it on WeChat. And then overnight, several companies started to contact us and asked for, oh, can we have this? What is this? And but actually, we had no idea that it could be useful for so many people. And then, so this was all before we started the company. Then we got back in touch with these companies. We also started to visit them, and they further explained to us what their exact needs are. And this was the time where we understood, okay, here might be room to turn this into a business.
Yeah, I see. I would be interested, Martin, from your point of view. That sounds like that, especially the Chinese market or the Chinese industry or people in general, they are much more, let's say, proactive when it comes to seeing and adopting new solutions. So how would you differentiate the Chinese market, especially the EV market, which is like booming right now, or like also in the past couple of years, versus the Western market, so to speak? What's the difference?
Yeah, there certainly are differences. I think one of the differences also comes from the age of the of the institutions and of the companies. So the EV companies, they are very young. So often when we work together with the EV companies, the engineers, the whole group, they are younger than me. They just freshly graduated from university. So there's no legacy that they carry along with them.
I see.
So I think this makes them a little bit more open, and they also like to play with the technology and just see what it can do. And in Germany, you often hear, we have done this for the last 50 years like this, and it has worked fine. So we keep doing it like this.
Do you still think this is a problem, especially in Germany, which is like known for its like excellent engineering companies, especially automotive companies? Do you feel this will become an issue or already is an issue for Germany?
I think it has been an issue in the past years, and we have seen the results of it. But my feeling is that the companies are really waking up, and that this is rapidly changing here also.
Yeah. When we talk about the method, obviously, when you did your you have the academic background, right, with your Chinese friend and co-founder, what actually convinced you that your method is the superior method compared to all the other things? Like when we talk about speed, accuracy, etc. Maybe you can name a few of these USPs.
Yeah, actually, at the beginning, we did not even know what it could be used for. So the strength of a particle method lies in the computation of when you have free surface flows combined with moving bodies. So, and this special combination, this is something that is very hard for traditional finite volume methods where you have to carry along your mesh. There are some solutions to it, but they are very, very slow because you always have to like recompute and redraw your mesh for every time step that you calculate. But at the very beginning, we also did not know what like the killer application of this was. So this we just found out by talking to customers. At the beginning, we thought it might be in casting processes, but it turned out that killer application is in gearboxes and electric motors, because there you have exactly this type of combination of moving bodies that even like intersect with each other, and also free surface flows. And I think this combined with the boom of electric vehicles and also the rise of GPUs that enabled this method to be used in an industrial scale, this kind of the stars were aligned perfectly for this method.
Yeah, really good for you guys. I'm wondering from the mathematical point of view, can you maybe give the audience, I know some will be interested in this, kind of the difference between the classical, let's say, finite volume approach versus the particle-based approach? Like, what is the actual difference? Is it similar? Is it way different? What is then also the pros, but also the cons that follows from this mathematical formulation?
Yes, so the mathematical basis is exactly the same. It's all Navier-Stokes equation. And we are also solving it on the same scale as your traditional finite volume solver, for example, like OpenFOAM. So equations are the same, but the discretization method is completely different. If you look at a finite volume method, you draw your mesh, and then you discretize your Navier-Stokes equation around the cells that you discretized before. So you always have your balance equations around this fixed volume. This leads to a problem if your geometry changes, because then this discretization also has to change. And in the particle methods, we changed the perspective of how we look at the fluid. So we do not discretize by volume, but we discretize by point. So these methods here, they are often called particle methods, but I think this is actually a very misleading term, because the people then look at these particles that they see as like something like water particles. But actually, they're just the discretization points. So we discretize our fluid domain along these points.
Okay. What is the actual pro of that, and what is the con of that? Because every advantage comes with a disadvantage, right? So what is the pros and cons of it?
Yes, the pro is the freedom that we get in terms of free surface flow and changing and moving, morphing geometries, because we can adapt very easily. And the con is to it that although we do not have to recompute a mesh, we still have to recompute neighbor relationships between these discretization points. And this is quite compute expensive. This is one of the compute bottlenecks of this method, that also after every time step, you have to rebuild the relationship between the one particle that you want to discretize and then its surrounding particles that are used to form formulations for gradient and Laplacian term that you need for discretization.
That makes sense. But then in the actual practical application, Martin, I'm thinking, like, what is the actual benefit that engineers get from your tool, such as shonDy, shonMesh, and you have a couple of others, right? Like, what's the actual benefit? Because I don't think they care so much about the mathematical formulation, but actually, can they use it in a fast way and as accurate as possible? Did I miss anything?
Yeah, exactly. This is something that is very sad when you come from an academic background and you're very passionate about the technology that you develop, and then you talk to engineering companies that need to solve problems. They totally don't care about the method that you're using. They care about that super reliable tool that always works and where they know what they get from it. So it needs to be predictable in a good way for them. And so this is one of the core guidelines for us, that the tools need to be super reliable and predictable for our customers.
Yeah, that makes sense. I think from an entrepreneurial standpoint, Martin, I would like to be, or I'd like to ask you, how was it for you? Because I think a ton of work goes into developing such a software, such a tool. Like, walk us concretely through the steps, like how much work actually goes into developing this tool, validating it, et cetera, et cetera. Because I think people listening to this, they just think, hey, you have a tool, it's being developed in like a week, you have a user interface, bam, done. But actually, how much work goes into it? Maybe give us a little bit of insights there.
Yeah, so actually, we are working not on one tool at the moment in our company. We have 4 different tools that are commercially used at the moment. So we have this particle code that we talked about before. Then we also have a pre-processing tool that people can use to clean up their geometries. So this is a completely separate tool, a separate group in our company that is developing it. Then we also have a traditional finite volume solver. And we also have a tool that is also a little bit special to automotive industry. It's a combination of a thermal network and a 3D FEM solver that can be used for thermal analysis.
And so actually automotive companies are the perfect fit actually for what you're doing.
Yes, we grew up with them, basically. We started with this very niche product, this particle, let's call it particle CFD tool. And then we soon found out, okay, this is not enough for them. They also need to know more about the thermal behavior of the system, because if you look at the engineering that goes into electric vehicles from a drivetrain perspective, when we started, you had the gearbox and you had your e-motor, you had your control unit, and they were all separate things. Now they are becoming merged together in even more tighter spaces. It's called now electronic drive unit, or EDU. So what is becoming more and more important is the whole system aspect of this thing. So how do these parts play together? And that's where we saw, okay, this particle method, this is nice to have and it gives valuable insights, but to analyze this system, more is needed. And that's why we built the next tool, our thermal analysis tool.
That makes sense, Martin. The question is, did the clients come to you and told you basically, hey, by the way, can you also develop this? Or did you come up with the idea or by yourself basically and said, we're going to develop this and show it to our clients because they might potentially be interested in that too?
I think it's always a combination that we see where the problems are. We listen to the customers, and then we need to find out by ourselves, okay, can we do it? Is this something that is interesting for us and where we also have the expertise? And then we make small demos and then show it to them and then iterate with the customers and then build it out into full products that then other people also can use.
Yeah, that's super cool. Yeah, I mean, compared to other companies, I think what I really like about your approach, which is probably the more sane way of actually doing business, is you start from the first principle, but also from the problem of the customer and then develop the tool. On top of that, a lot of people actually build the tool and then look for people who might want that tool that they've built. So we've actually gone the right way.
Yeah, of course, we've also gone the wrong way at the very beginning, but then we learned from it.
Pretty quickly, though. At least you learn from it sooner than later, which is cool. In terms of like integrating your tool into the existing tech stack, I think this is something a lot of German companies are always thinking about. We talked about this, Martin, right? Never change a running system. You already have a tool stack. What makes your tool easy to integrate into already existing workflows?
Yes. There's one super cool standard that was developed, I think also by German automotive industry. It's called FMU, so functional mockup units, or the standard functional mockup interfaces. This is like you can think of it as a package standardized format where you can put your simulation tool inside, and then many other simulation tools can just use it and run, for example, co-simulations with it. So this is something that we support in some of our tools and are currently building it into all of our tools to make it more easy to integrate with them. Then another thing that we did from the very beginning is that we keep all our configuration files open to the customer. So they're very easy readable files. Most of them are just JSON format as the input. And as the output, we also use very standard formats, VTK or XDMF formats, which makes it super easy to use other tools, import the results into other tools. This sometimes also comes with a trade-off, because when people have something open, they like to play with it. But I think the trade-off still makes sense for the customer to have this freedom and look at the files and interact with the files directly.
Absolutely, yeah. What about the validation bit, right? I think people who listen to this would also be interested in the validation side of things, which, by the way, you can also probably find on your website, I believe, like a lot of validation cases and case studies. Walk me through that process, how you actually validate a software such as shonDy.
Yes. We come from the academic background, so the first thing that we do is look in the open literature. There are so many experiments on heat transfer, flow experiments, countless things that you can find in open literature. And often these experiments, they also have a very simple scope. So the geometry is simple because they come from academic background. So they are great for first validations of your tools. But this is only half the story. This is also something that we had to learn the hard way. That because your tool can pass these academic tests and matches well with the experiments, does not mean that it's ready for industry use and also matches the expectations and what the customers know in real industry cases. So, for example, in one of our first customers, we were even not able to import the geometry that they constructed, because it was just so complex, and we could not even imagine how complex these geometries would get. But yeah, back to your validation question. Our customers, they often have experiments by themselves. So they make experiments in-house, and then they compare it, they benchmark the software. Almost nobody is just buying software and believing you that it's super accurate. So they will do a benchmarking phase. They build a simple experiment by themselves that is representative for their case. And then they do comparison calculations and see if it's within the margin of error that is useful for them to further develop, and also then get rid of some of their experiments at least.
Mm-hmm. Let's say the simulation wouldn't match with the experiment. How do you personally, Martin, approach the debugging of that problem? Do you do kind of the divide and conquer approach? How do you think about a specific problem? Because I think it would be great to look into your mind, how you guys are actually working on a code like this.
Yeah, the divide and conquer is always a great strategy for everything code related. It's always isolate the problem, and then even isolate this problem even further and see if this small problem in isolation now can match with the result, or if it makes sense. And then from these small puzzles that you build, then you can look at the bigger picture and see if they still play together in a good way. If you fix one of the isolated problems, and then you have solved the whole problem.
Mm-hmm. Walk us through some of the case studies that you guys have produced. Like, I mean, we talk about water wading. We talked about gear lubrication yesterday. We had a demo from Moritz live on LinkedIn and YouTube, where he showed kind of how easy it is to actually use shonDy. But any other case studies you can talk about? Yeah,
what we most of the time do is related to automotive industry. So the interesting cases are the water management cases. There are often things like sealings, or also strong condensation inside of the windshields. This is something that the customers care about, and basically water condensates on the inside of the windshield, and then they somehow need to get rid of this excess water.
Interesting. In general, about the Chinese market, how do you foresee the development in the next 3 to 5 years compared to the German automotive market, or like in general also the US market? And what what do the Western companies have to do in order to catch up with China, if that's even possible? Because if some of you might know, and Martin, you probably know this better than anyone else, is the time to market has actually to be shrunk from 5 years down to 3 years, right? So by 2 years,
At
you have to
least,
actually
yes.
have saved minimum, right? So how do you actually achieve that? One, definitely using the right tools. Do you have any other recommendations for people maybe listening? Maybe if even people from the automotive industry listening to this show or to this podcast, maybe some recommendations from your side in order to adapt quickly.
Well, I think I'm in no position to tell the German car companies how they can accelerate. I think that this is totally out of my scope. And all I can do is like observe how we work together with these companies that move really fast. And what we see is the great work ethics. So, really, really working a lot and also really caring about the product and making the product better.
Yeah, I see. Okay. The very conservative answer, which I also like. So appreciate that. When we talk about key KPIs, can you talk about concrete numbers in terms of time saving, cost reduction, speed to market, which probably are some of the most relevant KPIs for these C-level executives?
They're difficult for me to get because we don't get these KPIs from our customers directly back. They do not tell us how much did they now save with our product, because then we could also raise our prices accordingly. So all we can do is try to keep up with them. And we see that their development cycles are super short. And also in these development cycles, for us, the biggest problem is if new feature requests come up during their development cycles, because then we also need to be in the same speed. We need to be developing in the same speed. And I think a big problem or big difficulty for a software company is to still keep the quality and keep your release process in a very standardized and organized way, but still be able to adapt to all the customers very, very quickly. So this is like the big challenge for us, or the thing that we always try to optimize for us.
I see. Yeah, that makes sense. Going back to a little bit of the academic side of things, like if people watching this, right, people who are inspired by this talk, they also want to delve into fluid mechanics, maybe even smooth particle hydrodynamics. And how would you get started? Is it just picking a specific problem? Maybe we talked about academic problems, right? The classical canonical use cases. What is your recommendation to get started? It's just get started, pick a use case, pick a problem and solve it? Or what would you recommend also if people want to write their own code, like a little Python code or MATLAB code, whatever?
Yeah, what me really got into programming CFD codes was OpenFOAM. I think OpenFOAM is a great tool. It's a gift to humanity, basically. It's a great source for learning, not just from the fluid dynamic side, but also you learn very good coding practices. Although the code base is now really showing its age, also there are a lot of projects that try to modernize it now. But I think it's still a great resource to look at and just learn from the existing codes. In OpenFOAM, it's also great that you can just take an existing solver, try to make it run first, and then do some small modifications to it, and then learn from there. I think this is really, really helpful.
Absolutely. Yeah, that's good advice. What are you most proud of, Martin, in terms of the key achievements when it comes to shonDynamics, or maybe also outside of shonDynamics?
Maybe I can divide it into two things from a technical perspective. I'm really proud of how we achieved the combination of the 3D particle method with a 1D system simulation, so that we are able to take the simulation results from the 3D and just directly make use of them in 1D system analysis. But this is the very technical answer. From the other side, one of the proudest moment I had at our company was when one of the guys in our Chinese office, he was showing me his new car. It was the first car that he bought. We went down to the garage of our office and he showed it to me. And this was one of the cars where our software has been used in developing the drivetrain. So this kind of closed the full circle, and this was a really great moment.
That's pretty cool. What about in terms of partnerships? Any future vision that you have for shonDynamics and the team?
We have a lot of partnerships. We often outsource development if it's things where we are not really good at it, and we know that some research institute is very good at it. We outsource this development. For future outlooks and partnerships, we have a lot of technology partnerships with different research institutions where we see not our core competence, for example. And then we outsource projects and then later integrate this into our products. For the future, we are expanding our product portfolio. At the moment, we have 2 new products that we did not launch, but that are already in development for over 1.5 years now. And I hope we can release them at the end of this year. And they are going more into the design space. So not so much on the analysis side where we are right now, but more in like one step earlier in the product development phase in the design.
Now you made me a little bit excited. Is it something related to topology optimization and AI or something else?
It's not related to topology optimization. And I think AI is too big to nail it down to just one product. AI is creeping into all of the products. So at the moment, we are also integrating AI in some way or another in, I would say, almost all of our products. So the obvious way is like the communication side of the products. So I'm pretty sure, of course, nobody can predict, but I'm pretty sure that the way we interact with our CAE tools will completely change with AI models and the large language models. They will just talk to our software. And for this, we have to make our products ready. And this is what we are doing. And then like also not on the interaction side, AI will affect the CAE engineering tools, but also on the numerical side. And there we are currently also, we have the first tests with some special selected customers that we have a really good relationship with. And they are trying out our first particle solver that is using AI technology to speed up the pressure solving, for example.
Okay, now you mentioned something interesting. Tell us a little bit more. So basically, when we talk about AI, Martin, I think you nailed it. It's like a very broad term, right? What is actually possible? Like you talked, first of all, you have 2 pillars, right? You talked about kind of the acceleration of existing methods, but then also how engineers work in the future. Do you believe that the combination of AI agents, or like just AI in general, and engineers will actually make a difference in the future? And who are the engineers who will thrive and survive in the coming years? The ones who actually learn about AI, and how do you learn about AI? What is your recommendation, especially for engineering?
I think exactly this communication layer of the tools, this is exactly where the agents come into play. Because I think the agents, they will actually operate your CFD software. So you can imagine, like you tell the agent, I have this optimization problem. And then the agent, he will just set up the CFD simulation. You can tell the agent maybe, okay, here are my geometry files. And then the agent will do the setup of the simulation for you. And another agent might then do the analysis of the simulation results and then put it back into another program, maybe from a completely different company. But that is also has these capabilities to talk to the agent, and then the agent will just like orchestrate, I think, a lot of different CAE tools together for you in a way that is very tedious for people at the moment.
Yeah, I see. The pressure solving part that you mentioned, can you go a little bit more into detail, of course, without giving away kind of a secret sauce? I think it would be interesting for people to learn why even pressure solving. What's so critical about this?
Yeah, in the way we treat the Navier-Stokes equations, we need to solve a pressure equation. This is like a big system of linear equations, and this also takes the majority of the time for one computational step. So at the very beginning, I mentioned the finding of the neighbors is one pillar. And the second thing that is also super expensive from a computational point of view is solving the pressure equation. So we are always looking for ways how we can speed this up. And this is also now ongoing research for maybe, I would say, at least 4 years at our company, where we try to find out different ways how we can speed this up. Many ideas have failed until now. But now I think we have something that works pretty well, or at least it has some usage for the customers, that we can really speed up the simulation. At the moment we lose a bit of accuracy. So again, we have this trade-off of speed and accuracy, but we gain a lot of speed. And maybe a small technical detail, what is interesting or what has not worked for us. We try to build general models, like general AI models, where we feed in a lot of simulation results. This has never worked. And now we are doing it more fine-grained, that part of the training is also part of the solving process, basically. So it's like a direct feedback loop between training and solving.
That's super interesting. I'm really looking forward to see where your company is going in the next coming years, Martin. I think you're doing great work. I think we'll show the tool more and more to our kind of listeners and people watching the podcast, right? We had the deep dive session. There will be more use cases coming, especially when it comes to 1D modeling. But Martin, thank you so much. We'll definitely hear more from you in the coming weeks or months. And I hope we have a second part of the podcast where we talk more a little bit about the AI method that you guys are using and implementing.
Yes, sure. I'm looking forward to it.
Awesome. Thanks a lot.
Bye-bye.